Thank you, Michelle, and thanks for having me here today. I see John has already posted some presentations, so you can check those out after this one, see how they compare. It's great to be here. Notice I'm actually speaking tomorrow on this. I forget that July 11th just kind of shows you how we're in a time of lots of things going on. Lots of, and I'll give USBI a shout out. Incredible from 7-8 years ago when I started getting involved while I was at EPA running water programs and focused on the Chesapeake Bay and green infrastructure and stormwater and all those things of where this whole arena is today in terms of research. And I'll mention that when I talk about the biochar workshop sponsored under STAC, some of the findings and some of the recommendations, the proliferation of research, and thanks to the R&D folks out there, keep it up, we need it. It's an interesting science, to understand how these different biomass and biochar sources work. But today I'm going to talk about, trying to advance these slides. Not sure why this is not working. Michelle, got any? Oh, here we go.
There you go. Yeah, I was going to say maybe your arrow key too. Sometimes that works.
Thank you. What I want to talk about today, and it's amazing how much there's to talk about. It's good to know that a number of you are already familiar with biochar, but also a number of you are interested in it. And so I'll talk a little bit about what it is in the context of this presentation, addressing stormwater use in green infrastructure, the Chesapeake Bay, but starting with the state of the Bay. Where are we, and why is this topic so important? As well, where are we in terms of sustainable stormwater management? What do we mean by that? And how does this impact climate, as many of us are trying to stay cool today? I saw that out west in Nevada and California, they're into the 128 is what I saw, I think, somewhere out in maybe Nevada. But heat index is challenging throughout the country. We've seen the devastating storms in the Midwest. Temperature up and down. I'm sorry, extreme weather has been up and down, but we certainly are experiencing something that is highly unusual as attributed to climate change. And how is that impacting our water bodies? In some places we have no water. But how do these types of practices address those extremes, both from reducing volumetrics as well as recycling and being able to reuse, treat and reuse that water? Biochar 101, I'll talk about that and multiple benefits of biochar, why I've been so excited about it since I learned about it many years ago, and continue to learn through all of the R&D that's happening, how it enhances bioretention performance. And I'll share some case studies. I was unaware that there are many places that are already using it here in the Mid-Atlantic, as well as other parts of the country, that have been evaluating its use in bioretention in various settings. The Biochar Stack workshop report and recommendations I'll share. And then, of course, scaling. We have opportunities to scale and save the Bay. And to end off with some summary and final remarks. So state of the Bay, Chesapeake health and importance of sustainable stormwater management. We know, of course, the importance of Chesapeake Bay health, just like many of our great water bodies throughout this country, ecologically and economically, the importance, and of course, the challenges of legacy pollutants. Nutrient pollution has been a legacy pollution. for many of our water bodies, whether you're talking about the Chesapeake Bay or the Great Lakes, certainly the Mississippi. And of course, that's as we're challenged with a lot of soil loss and loss of phosphorus and reduced phosphate supplies. They're all getting washed out. How do we get better at this, given we need nutrients in our soil? And stormwater runoff has been an impact because volumetrics have increased and have scoured our stream systems and therefore the bay. And of course, we have legacy toxics like heavy metal in the Chesapeake Bay. Mercury has been an issue. We have emerging toxics that actually have been around, but if anyone's heard of forever chemicals, PFAS as a class, and of course, climate change makes everything worse. So just yesterday, if you were paying attention to the news, there was a State of the Bay, the grade came out, and the headline, in fact, I saw this last night, overall health of Chesapeake Bay gets best grade in more than 2 decades. So last year was a C, and this best grade in 2 decades is a C+. Improved, but still not quite there. The watershed health scored 52%, our greatest C. Similar last year. We still need to pick up the pace. And in fact, to date, since 2009, current state of nutrient reductions is 17% in nitrogen and phosphorus since 2009. And it's nothing like seeing what the actual volume means in terms of that target goal as well as the reductions. So that 17% represents going from 297.9 million pounds in 2009 to 247.6 million pounds, where we are that need to be reduced, okay, in 2023, meeting 57% of that original goal, which was per this total maximum daily load, TMDL, that was done a number of years ago. And let's be reminded, 2025, well, we're almost halfway there. So we've got to look at these kinds of next generation approaches, such as what we're talking about, the use of biochar in order to improve the health. And it really amounts to healthy soil. As indicated, we've had a lot of erosion, sedimentation with the increased intense storms. If you've got poor soil health, and we have poor soil health everywhere, in our ag lands, in our urban lands, we've essentially in ag applied lots of chemicals, and we've moved towards big outcomes in terms of product. We've destroyed the soil. And that's why I'm going to mention later on in a bit, USDA NRCS is now paying farmers to add that carbon back to the soil through compost, but also through biochar. So as we look at the volumetric impacts, which are exacerbated now, USGS did a study a number of years ago and modeled to determine the impact of low impact development or green infrastructure and how it can improve performance and reduce the volumetrics, and found that it could, could significantly improve or reduce those volumetrics as compared to, so this would be decentralized distributed green infrastructure versus centralized gray infrastructure, and that it would have a significant improvement. And we've seen broad implementation of green infrastructure. For those of us who were working on green infrastructure back in the days when people doubted and questioned, and we were really trying to show the benefit, how it worked. And I think we'll continue to look at different designs, but these are rain gardens, bioretention, This is green roofs, and many of our Bay states, and particularly, for example, in the district, have significant BMP implementation along those lines. So sustainable stormwater management is utilizing green infrastructure and tailored biochars. And what I mean by that is, depending upon the setting, for example, in the Anacostia watershed, while at EPA, we implemented a number of heavy metal TMDLs in these local waters, meaning heavily, dense, impervious areas, urban landscapes. Runoff was, in fact, not all about nutrients, but very much about toxics, for example, that come from automobiles, deposition, cars. And so you get this mix of pollution, particularly in these areas. But again, we're finding that, many farms have impacts from pesticides and toxics, and now PFAS. Biochar has been found, and when I say biochar, I'm going to talk about a broad category of chars, because different chars, based on the biomass source, are better to treat different types of pollutants, as we've found. But so the class, we've seen, the ability to reduce nitrogen and phosphorus by up to 98% or so in stormwater, and heavy metals similarly, 99% or so, and also PFAS and work that I'm currently doing with Stevens Institute of Technology. In addition, the benefits of using biochar, we're seeing opportunities for credits and subsidies. So investment in biochar can mean money back. USDA has a code 336. It's a soil carbon amendment. They're now actually providing financial assistance, is what they call it, for putting carbon back into the soil. Typically 60% compost, 40% biochar. I'm sorry, 60% biochar, 40% compost in 2023. And this is an average, because it really varies state to state. I believe at this point, just about all of the states have adopted 336, but not all of the states have implemented 336. And it roughly $160 per cubic yard is reimbursed back to the farmer. This can be used on farmlands or forested lands. So there's money back, and that carbon is helping to regenerate the viability of that soil. And also the carbon increases the soil's ability to hold water. So in a drought, very important, but later on you'll see that water also helps with denitrification and bioretention. Nutrient credits, Chesapeake Bay, these are some averages. You can see it's a broad range, but again, the use of biochar to treat these nutrients. There's also the ability to kind of look at that biomass and processing it into biochar and reducing the nutrient loadings. Nitrogen is going for anywhere from $2 to $20 per pound. So if you're looking at a ton reduction, that's anywhere from $4,000 to $40,000 per ton that could be reimbursed or additional money. Phosphorus is $30 per pound to that amounts to $8,000 to $60,000 per ton. Again, investments in char, helping to get those kinds of reductions. There's the ability again to look at these types of monetary credits. For communities, that's money back. That's a reduction in your investment, and it's also cheaper. I know green infrastructure in some places will, 1 point per acre to reduce nutrients in urban areas was as high as $300,000 to $500,000 per acre. Here's a much more cost-effective way to still get those reductions. Carbon credits now, biochar carbon removal. Again, USBI site has a lot of information on this. So I'm just sort of summarizing. You can go to the site for more information. But in 2022, BCR accounted for 87% of total carbon removal deliveries, and much more cost effective, lower than any of the other CDR approaches out there, and on average, 179 per ton. So in terms of back to sustainable stormwater and biochars, this is a graphic that I created probably a few years ago. There was a lot of interest in it, looking at sort of this corridor of different landscape types and land uses, and the ability to really introduce biochar for improvement in all of these areas. And at the end of the day, as I mentioned earlier, it's about soil health. Healthy soil is healthy water. And together, healthy ecosystems means healthy communities. So this is really just getting at, back to that USGS study, if you can capture and treat rain where it falls instead of having this runoff that introduces pollutants and sediments into water bodies and reduces the quality of the water bodies in those their aquatic systems, it's much better. And we can do that through the introduction of biochar. We can actually improve those green infrastructure practices. So this just sort of looks at the different ones, which could include, amendments in green space. We've been supporting riparian corridors throughout the Bay, but with climate, as I've talked to communities in the Chesapeake Bay, they're saying our riparian corridors are getting blown out. Biochars actually help to quickly establish those root systems and improve those riparian corridors. If we're looking at, in fact, green roofs are wetlands and constructed wetlands. I'll talk about studies where biochar has also improved the performance of those wetlands. Over time, ponds, in fact, which was the first order of stormwater treatment in this country decades ago, we're finding that, there's probably over 1 million of them in the Chesapeake watershed alone. They've not been maintained. However, no one wants to clean them out because of all the pollutants in them, many of which now classify as hazardous waste. The introduction of char can reduce those types of impacts, but also reduce the amount of runoff. So this is just a summary, again, of some of the things that I've mentioned before, and I'll get into the improvements in terms of infiltration and pollutant treatment, removal efficiencies, including those for nutrients and heavy metals, and of course, nitrification, denitrification processes, which is where biochar helps enhance microbial activity to do the job. So here's a review of some of the things I've said essentially. So I'm not going to spend a whole lot of time on this slide, but it gives you an idea of the types of functions of biochar and why it works. So there's a physical aspect to it, and there's a chemical aspect to it, and of course biological. Physical, surface area, high porosity. However, chemical, cationic exchange capacity. They're mostly anionic, meaning they have a negative charge. They can be functionalized to kind of change those charges in order to treat certain pollutants. But for example, that negative charge is what makes them so great for heavy metal removal. And you can see the porosity there is also what helps with microbial populations. So you'll get biofilm development, and with those microbial populations comes nitrification. You can actually reduce ammonia, and then of course denitrification as you get can create anoxic, down in these biofilters, anaerobic conditions. So, and that means lack of oxygen. Certain types of microbial populations that are denitrifiers can treat that. This is just a summary. For example, pH matters. A lot of science is important in this. And if I'm talking kind of past some of you, pardon me on that with the anaerobic and aerobic, but it's to give you an idea that chars can help enhance, as we look at nature-based approaches, can actually help enhance nature's ability to treat many of these pollutants. And if you really think about it, over history, we've essentially used soil and water to dispose of pollutants. And we eventually came to find, dilution is the solution to pollution. Well, now we've got water bodies similar to where our property is up in Passaic and Hackensack River in Newark. Both are Superfund sites now. Same thing with our soils, because of the carbon and organic matter now, which has been eroded, and while we're adding carbon back, we found that, we get attached pollutants to that. Biochar can help to return and regenerate those resources. So the types of environmental treatments, biofilter and retention, which I'll predominantly be talking about today, but also how those biofilters and bioretention demonstrations and green infrastructure have been able to reduce pathogens and bacteria. It's by filtration, infiltration, and treatment. And of course, I've talked about some of the chemical aspects of that. So this just is a summary slide of the various ways to use biochar that actually go beyond that of stormwater. In many cases, it's being used for Superfund sites and for soil remediation. In terms of enhancing bioretention performance, for those of you, this is a cross section, for example, of a bioretention basin where you have the different amendments that make up that system. And biochar-amended media, where it's typically used, and you're seeing kind of that upper section of this is typically you're looking at 24 inches, etc., a sand and gravel layer, and usually there's a 20% amendment that provides organic or nutrients, which is really what the microbes need, to be able to grow and help in improving the performance and the viability, of that soil. So before eventually infiltrating groundwater so that you've got a cleaner infiltrate. So this is just another, look at that bioretention system or rain garden, for example, and the importance and what biochar does. So the top one is a typical bioinfiltration system. And you can see the bottom one, which is where that's been amended with char, increases resiliency to stress. It improves porosity, so you get better. The char helps improve porosity, you get better infiltration, you get quicker establishment of root growth. The vegetation we know is important for the treatment, but with typical bioretention systems, they've not been found to treat dissolved pollutants, which is very important in terms of really being able to improve that water quality, whereas the addition of biochars are helping to address and treat those dissolved pollutants and enhance that contaminant removal. The char serves as a carbon source as well for the microbes to do that. So I wanted to give just an example of typical stormwater bioretention soil mixes, ratios in the Chesapeake Bay states. That crosscut that you see typically, you can see it's 50 to 60% sand, 20-30% topsoil. And then of course, there's got to be some organic material, as I mentioned earlier, in order to really expedite the microbial growth to help do some of the work of treatment. And those notes just indicate why certain states have certain mixes, because they may have a reason to have a higher sand mix. Peat has been used in certain areas, but of course we know peat and other materials that have been used in some treatment are not climate friendly. In fact, the biochars have been compared to granular activated carbon, which has been the treatment of choice for toxics. But granular activated carbon is made from bituminous coal or coconut, high temperature, not climate friendly, expensive. And these are, I'm going to call the biochars sort of the greener, activated carbons. And what's great about it is we're taking waste biomass and turning it into a beneficial reuse. Big deal, because waste is a big problem. And we have a lot of sources of that biomass. In most cases, you're looking, when you see biochars being applied, particularly with stormwater, it's wood chars, because wood chars there's no concern for leachate they don't contain as much nutrient. In fact, if it's added to a soil that needs nutrients, you usually have to add something if you're using a wood-based biochar. And so the idea here is, all right, look, compost leaches, we know that. We found that compost leaches, it was always the way to go. Everybody uses compost, but depending upon that source material, we found compost leaches heavy metals like copper. We're finding compost is leaching PFAS. But however, you add the char, and actually could make a very nice combination, because the char can take up that leachate, like for example, heavy metals, and the compost provides the nutrient that together with the char makes for helping with a regeneration of a healthy system. But I wanted you to see in the center there the typical nutrient values of this bioretention mix, nitrogen, phosphorus, potassium, and then how these chars compared. So it's a busy slide, but if you look at the green versus the red, you'll see, for example, poultry char is a lot higher. Cow manure char, actually, nitrogen is right in that mix. Phosphorus is close. It's not high. It's close, but I will tell you, studies have shown that cow manure biochar does not leach that P, and it makes a great amendment. But you can also think of and look at the hardwood biochar. It's low on N, but P and K is right in there. Softwood biochar, very low, but you can also do blends. So if you look to the right, I played with blends, and we're seeing some blends happen in cases, but this is really beyond stormwater. You can also think about this if you're looking at trying to bring back healthy soil for example, in a riparian corridor. But I think what I'm interested in is, how can we treat heavy metals and nutrients through these blends? And that's what we've been experimenting with. Here's an idea of surface area. Wood chars tend to have higher surface area than manure chars. Pardon me, I'm going to call them chars. Porosity, the manure chars tend to have interesting, it depends on the char, but if you compare the porosity, they're very similar. And of course, it also depends on the source material, both for wood and manure chars. Some manure chars have large pores, not as many on quantity, but on size, which is what you don't see here. Particle size, you can see wood char 1 to 10, 1 to 5. So it's just to give you an idea, comparing them. pH levels, the manure chars tend to be higher in pH, which is why it tends to also make them better for treating, for example, lead and heavy metals. We've tended to add for acid type soils, acid mine drainage, for example. We've tended to use lime to reduce that pH. In this case, you can use a poultry char in that soil, not in the water, but in the soil, for example. Cation exchange capacity, because manure chars, if you think about it, the source of those manures and what that animal ate, you may have more minerals. So that CC tends to go up, which means they have a stronger binding capacity, you know, for particularly if you're trying to treat something cationic. And then a carbon content, wood chars tend to have greater percentage of carbon than manure chars. But again, this is a very general, you really got to look at those individual chars, and that's why the science and the data is important. Water holding capacity, very similar. Again, it's the larger pores that help the manure chars. And then of course, large surface area and lower moisture content starting with wood biochar tends to really increase your water holding capacity. So I want to move through a few, quickly through some of these studies that are being done using chars to amend green infrastructure bioretention. Shout out to Dr. Imhoff and Del University of Delaware years ago, started working on amending, in this case it was a stormwater pond, but they've done swales and have been able to, and this is using wood chars, been able to reduce total nitrogen. Again, remember this is dissolved up to 73% and phosphorus 9%. So very effective, and also improving soil health. Anne Arundel County, and this roughly 5% char. It's very similar, 75% dissolved nitrogen, 85% phosphorus. Again, continued monitoring to look at the effectiveness. Philadelphia, Green City Clean Water's use of green infrastructure to address their CSOs and beyond, have also studied the addition of char, bioretention, 5%. So you see very similar numbers. So we're seeing consistency here. Again, these are wood chars, 80% P, 70% N. And then just a summary of those in terms of what they did with heavy metals, very similar. Anne Arundel and Rain Garden, lead 75%, copper 85%, zinc 90%. Del Dot project, this was 10% char by volume, got 65% reduction of lead, 80% reduction copper, 85% reduction zinc. And Philadelphia, 5%, got 70% reduction lead, 75% copper, 88% zinc. Just thought I'd throw out something from out west. And again, I think these studies over time, there's the ability to amend, what's being used, or go back and treat the char, activate the char to get the types of target reductions that are desired. But this one was, again, urban bioretentions, 5%. Nutrient reductions were in the 30 to 40% range. Some of the other studies may have used activated, like steam activated wood char gets better results for wood. Heavy metal reduction, 60% copper, 70% zinc. And this is a study that I really wanted to kind of focus on because it really evaluates the importance of the combination. And this was wood char actually processed at 900 to 1,000 degrees. But this was a dairy farm, and the interest was using bioretention, a vegetative bioretention system to treat nitrogen, as well as fecal coliforms, fecal bacteria, of course, coming off that farm and the lagoon, and finding that the vegetation really enhanced with, the ability to treat that runoff. So it's kind of getting back to what I was talking about at the beginning about the importance of how you bring green infrastructure together with char, and then of course the microbial activity that really helps to improve performance. So quickly, if you look, ammonia was reduced by 92.5%, and total nitrogen was 98.5%. I believe phosphorus was very similar, but significant reductions in E. coli and enterococci. So again, the multi-beneficial aspects, the biochar with the plants. So let's talk phytoremediation and microbes, had synergistic effects to get the multiple types of performance reductions there. So why am I talking about manure-based biochars when we see the great kinds of results with the wood-based biochars? Well, I think if we're going to be sustainable, you got to look at the biomass that's in that region that you're trying to figure out what to do with. And in the Chesapeake Bay, estimated total manure production 60 to 70 million tons annually. That excess manure contributes to nutrient pollution, particularly nitrogen and phosphorus. And despite having implemented lots of nutrient management plans, there's still a significant portion of manure produced that exceeds the nutrient needs of crops and soil. In fact, about 35% of the manure produced is excess. That amounts to 24.5 million tons annually. Just comparatively, whether you're looking at a gasifier or a pyrolysis unit, and we've got a lot of activity now because of interest in biosolids and sludge and PFAS, and EPA has actually determined that pyrolysis gasification at temperatures of 600 Celsius above, 600 to 800, can destroy PFAS. Well, let's look at this. In 5 years, this is sort of a general range. 25 gasifiers can process 1.8 million tons of excess manure for about 70 to 80 million dollars. According to the Chesapeake Bay program, about 283 million pounds or 141,500 tons have been removed in the past 10 years for a cost of $5.8 billion. So let's do the math. Maybe we need to revisit some of this processing, and whether you're putting it back in the soil, like Cornell found that biochar from dairy cow manure reintroduced to the soil was more effective in soil health and regeneration than manure land application. So this is, and also you're reducing greenhouse gases, you're mitigating methane, which we know is an acute gas, nitrous oxide emissions, and of course, importantly, sequestering CO2 levels, and reducing that runoff helps to reduce algal blooms, etc. This is, shout out to Cornell and Akil Enders. This is Akil's slide that I borrowed that actually shows, if you look at from their study, that for cow manure char, in terms of leachable, it's not leachable, minus 91%. There's 13% of availables, predominantly bioavailable. You can see some of the other elements in there and why we've also seen cow manure biochars behave very well in terms of treating heavy metals. This is from some of my own studies with Stevens Institute of Technology's Environmental Engineering Lab, where we activated certain manure chars and were able to get really great, this is cow, performance in terms of nitrogen removal. You can see that it's in the upper 80s, 90s percentage, and these were at different temperatures, 750 and 900. Phosphorus removal again, we can avoid the leachate and actually get absorption. More manure biochar studies. This one was a different one. It was again activated 88.9%, 94 for 88.9 for P, 94 for N. Similar, you can see, and these are hydraulic studies. We also did the flow rates. From the flow rates 110 to 118 inches per hour. So very good flow rate. And this is just a summary of, where we have concerns for heavy metals as well as nutrients, why we might want to look at those amendments with these manure charts, because you can see as compared to the heavy metals removals that I shared from the wood chars earlier, these manure-based chars get into the 99% removal of those heavy metals. And we're also seeing very similar results in treating PFAS, where these manure-based chars outperform the wood-based chars. Both worked, but wood we saw in the 95%, these activated manures we saw in the 99.8% removal. And we're finding other beneficial uses for those greenhouse gas emitting biomass sources. These are the absorption capacities that we have. So you see both the absorption in to the left, nutrients, heavy metals, PFOA, PFOS, PCBs, we've got over 90%. And then the absorption capacities on the right. And then here are just some examples where we did blended chars, courtesy of Adam Maury here. This was a suburban farm. Biofilter that's treating pesticides, for example, and nutrients. And you can see very good establishment very quickly of vegetation, clear water coming out. This is a urban stormwater in the Anacostia bioretention basin, about 0.8 acres, and where we got a concern for heavy metals as well. And this is Green Street that we just did near our property, again, where we have legacy pollutants of every imaginable type of heavy metal, including chromium, mercury, nickel, cadmium. We've done studies on all of them in terms of getting great absorption with these chars, and we amended Green Street with some of this chart because we had a concern about treating these heavy metals and toxics. So now, just to quickly talk about the Bay workshop, using carbon to achieve Chesapeake Bay and watershed water quality goals and climate resiliency. Workshop was done last summer, early summer. Identified the science gaps in implementation activities and opportunities. And it was really about, how do we integrate biochars into the Chesapeake Bay TMDL watershed model to improve the state of the Bay. And in order to do that, leverage biochar credits in these BMP protocols. So the discussions focused on climate smart agriculture and forestry. Again, as I mentioned, the 336 from NRCS, that's paying farmers to put carbon back in the soil. Urban landscapes, which still need carbon, but also need a treatment for for these legacy and emerging toxics. Again, also, if you're planting riparian corridors, there's nothing like the char. You put the carbon back in, you create a carbon sink, you reduce greenhouse gases, you increase the ability to reduce volumetric flows, you help support the health of these water bodies and the bay system. And biochar production systems, we talked about the technologies. The recommendations, as summarized, and you can see this on the Chesapeake Bay site, the full report. Promote biochar research and development. Thank you, our researchers out there. Implement biochar in agricultural practices. We need standards and guidelines for stormwater. I mentioned that it's, it's a good substitute and why it makes so much sense. If you're looking at a 20% organic need in those systems, why biochar is, provides additional benefits in addition to treating dissolved pollutants. But we do need to increase public awareness and education, which is what this workshop, this webinar is about, and foster policy support and funding for these types of approaches, because at the end of the day, they could save us money and help us get there quicker. I just wanted to acknowledge the workshop steering committee, Jason Hubbard, West Virginia co-chair, and Jennifer Egan, University of Maryland co-chair, and of course, Chris Brosh, staff member, Charles Hegberg, Chuck, and Tom, and everybody here, Dr. Imhoff, Dr. Teal, David Wood, yours truly, and Ken Pantuck, Region 3. But we also had a number of experts who gave their time at the workshop from around the country, essentially, practitioners, NGOs who participated in that. So just a recap of the so what. Well, the so what in the Chesapeake Bay, we've decreased nitrogen by 17%. The target is next year, 2025. We're 57% there, and the target goal for a target goal of next year. So obviously, we need to look at these types of approaches that can be cost effectively scaled, that are climate friendly, and help with climate resilience. Biochar can reduce nitrogen, phosphorus, and toxics, as I've gone through the presentation, anywhere from 85, 98+%. Just in summary, it's time, as the Bay the workshop presented, there was over 30,000 peer-reviewed scientific papers on biochars that have been done in the past 10 years. We agreed, hey, look, in many areas, we already know enough. We need to go ahead and move on this. Quite frankly, in the stormwater arena, many of the practices that we've had out there, we don't even know if they really worked. And as I mentioned with stormwater ponds, they are now sources of toxic pollution. We know this can help. So there's great potential for scaling biochar. Biomass waste is abundant. We need the policy report, the funding. We need to work collaboratively. We need strategies on integrating biochar into stormwater management practices, but it was good to see that it's already happening on its own because it makes sense. And we need to increase outreach and, of course, applied R&D, scale up on those demonstrations. And that's it. Thank you. Let's see, 5 minutes.
Thank you so much. I want to jump into questions because we have some really great ones. And are you able, Dominique, to stay a little later to continue with questions if we go over the 1 p.m. mark?
Sure.
Because you have a hard stop.
Okay. No, I'm good.
Okay, we won't go too far past 1, but we'll try to get to as many questions as possible.
And I haven't seen the questions, but obviously we have a number of our experts on, I think. John, yeah. I know if you guys can also help answer some of those questions, if we can't get through them, that would be great.
They've been really great in the chat.
Okay.
I'll go ahead and stop our recording here for the Q&A.